Thank you, Pascal. So today I'm going to present the proximal policy optimization method. So first, this method is a continuous work of previous trust region method. And according to the OpenAI blog, the PPO has become the default reinforcement learning algorithm in the OpenAI because the ease of use and the good performance of it. And they are actually, the paper is by the same author from the trust region. And first, let's just recap some background. So in the class, we learn about the policy gradient method, which is reinforced. And this is the algorithm. And here, I want to mention maybe in practice, instead of updating the gradient in each time step, we usually update in each batch or each trajectory. And to keep inconsistent with the paper, I just changed the notation. So here, instead of G, the paper used A, which stands for the advantage function, and everything else stays same. So let's count the method. So what's the problem of this method? So I want to follow the intuition behind this algorithm and trying to find how can they come from the problem and to the solution. So the first one is the unstable update. So it's actually a very common question in the machine learning problem, but it's very severe in reinforcement learning. So suppose you are in a supervised learning algorithm. Once you update a wrong direction or too large step, but in the following correct label and data, we'll try to fix this error. But in the reinforcement learning, if you are taking a large step, which means you may get a bad policy, and since the new data and the new batch are generated from the current policy, you may get a bad samples, and from which bad samples, you may get a worse policy. So in practice, in order to get a stable update, we usually keep a very small step size, and which make the learning process very slow. So the next problem is the data inefficiency problem. So just a reminder that the policy gradient is an on-policy method. So it means for each new policy, in order to evaluate it, we need to generate a completely new trajectory for it. We roll out it in the environment, connect new data, and update the gradient, and we just throw out the data. So yeah, that's inefficiency. And since we are using like the neural networks, which need many update steps, so if you combine these two, in order to get a stable update, we need to set up a very small update step. And for this one, we need many steps and a bunch of data. So in practice, we usually spend most of the time connecting the data instead of optimizing. So how can we handle the first problem? So we get the data inefficiency, and how can we make it efficient? So remember, that's the goal of it. We want to evaluate the gradient of current policy. And yeah, so that's a problem. How can we avoid sampling from current policy? And one efficient way, like previous algorithm, like DQN, for example, we can use a replay buffer or experience. We are actually taking samples from previous samples or previous trajectory to estimate. But what's the problem? So the previous samples are generated from the old policy. We actually need the gradient of current policy. So that's a problem. So the first, can we actually estimate the expectation of this value from the one distribution, but without taking samples from it? And the answer is yes. In the statistics, there's one trick called importance sampling. So it's actually a technology. So you can estimate one distribution by taking samples from the other distribution. So for example, we want to estimate the distribution of this value, the expectation of this function f following the distribution of p. And we are estimated by taking sample from it. So we cannot sample it anymore. So let's write down the definition of the expectation. And we apply some trick. We multiply by q and divide it by q. So what's the result? So we actually reformulate it. So you see, we can take the samples from Q distributions and calculating the expectation of this value and get an unbiased estimation of this value. So it's theoretically equal, but in practice, we still use the sampling method. So we're taking sample from Q distribution and estimate the expectation in P distribution. So we got this method. So how can we apply it to the policy gradient? So this is the important sampling, and this is the gradient step in the policy gradient. So we just apply this to this one. So instead of sampling from the new policy, we can sampling from the old policy and multiply by the ratio. And this is the gradient value, and that's the objective function for this gradient. And in the paper, they call it surrogate objective function. So that's it. Yeah, so far so good, but is there any problem of it? The answer is there's no free lunch. So although these two expectations are exactly the same, but since we are using sampling method, that means the variance is also important. So that's the definition of variance. So we just write down the two parts. So the left part is the variance of left-hand side, right-hand side. So we expand it. So here, we just expand it, and you can see the green part is exactly the right-hand side of it. So we can replace it by the left-hand side. And if we use the same trick in the important sampling, we can transform the distribution Q to P. And that's the result. And here you can see the difference. So the only difference comes from this ratio. And you want to match the two distributions, which means you also want the variance also same. And if it's big, it means the variance are very different, which means we may need to sample more data if it's far away from 1. So currently, we can actually handle the data inefficiency problem. We can learn from previous policies. So next problem is unstable update. So how can we go from unstable to stable update? So what is stable update? It means we want to make some confident update. But what is confident? So just remember that the advantage function are calculated based on previous policy. So if the new policy is very similar to previous one, your advantage function can get a very accurate estimation. So we want to make a small adaptation of the policy. So one possible method is adaptive learning rate, but it seems not so well, works not so well in the practice. And another thinking is that, okay, how about limit the update range? So we can only update a few or a little on the policy so that it still keeps similar. And yeah, that's the question. Since the policy is the distribution of actions, so how can we measure the distance between two distributions? I guess almost everyone knows it. So we can use KL divergence. So in the KL divergence, you can calculate the distance between two distributions by this formula. And if we add to the policy gradient, the KL divergence of two policies lies in this one, and it exactly shows how different of two policies. So okay, we can calculate the difference between the policies. Let's just combine these two methods. So exactly that's what is trust region optimization. Remember, this is the surrogate objective function, and we want to bound the old policy and the new policy. In the KL divergence, it's bounded. Okay, so this is the idea for the trust region, and it's a very common trick in the optimization. So once you got a constraint in your maximize function, it's very hard to handle. And one trick is you take a Lagrangian dual of it. So instead of a constraint, you add it as a penalty. And you see, beta is always less, greater or equal than 0. If KL divergence is big, you actually add more penalty to your objective function. And according to the paper, the TRPO use a hard constraint instead of the penalty because they find that it's very hard to find a constant beta value that is suitable for all questions. Even for a single question, the behavior will change during the training process. So, okay, so let's actually also for the computation, TRPO use a conjugate gradient descent to handle the constraint, right? So they are approximate the invert of Hessian matrix, but you actually handle the Hessian of neural networks, for example. So it's very expensive both in computation and space. So that's the idea of the proximal policy optimization. So according to the result in the TRPO, the constraint does help in the training process. But the idea is that true that this is a strict constraint? So what if I just break one constraint in just one time in 100 update? So yeah, maybe does it matter if we only break the constraint just one time or a few times? And how about treat the constraint as a soft constraint? And we try to add the proximal value to it. So that's the first one, just the previous formula. You get the KL penalty on the objective function. So the problem is it's hard to find a constant beta, right? So how about using adaptive beta? And that's the first part of PPO method. So you calculate same gradient, but meanwhile, you calculate the KL divergence of two policies. And if KL divergence is too small, so here D target means the distant target you set initially. So if it's smaller than your target, it means, okay, maybe we can release the constraint so we can add more diversity on it. So we reduce the beta. And if the KL divergence is too big, means, okay, we need to add more penalty in the following trajectories, and we just double the beta to add more penalty on the KL divergence. Yeah, so the one problem is that we still need to set up an initial KL divergence target value, but it's much easier. So to summarize, that's the algorithm for the PPO with adaptive KL penalty, everything the same. So according to the importance sampling, we can actually sampling from previous one and taking k-step optimization in one update. And we just adaptive the beta value. Yeah, so another way of thinking this problem is that, for example, we want to maximize this function, but instead of adding the KL penalty, so for simplicity, I just call this ratio as R. And the idea is that since the advantage function is based on previous trajectory, so we can consider it as kind of stable. So the unstable part comes from this update. So if the new policy is very different from the old one, so the inverse happens. So how can we bound the update of this value? A very natural idea is how about we just limit the R within a range. So for example, we have a common R here. And when we update, we set up an upper bound and a lower bound of it. So we are actually limit the absolute value of R in a target range. So if we apply this range, you can see the R is bounded by the, oh, sorry, this is a typo. So by the 1 plus epsilon and 1 minus epsilon. Yeah, basically that's the idea for the second part of PPO. They use a minimum of these 3, which is exactly this one. So it's bounded. If R is too big, it's bounded by this one. If R is too small, it's bounded by this one. And everything else lies in this region, and which is exactly this one. So basically, this one is exactly this curve. So you actually bound the update of this objective function by a target region. And that's the summary for the clipped objective. So you can see that we keep all the framework similar like the policy gradient. We still calculate the gradient and instead of the Hessian. And also, it's very easy to implement this clip function in our current framework like TensorFlow or PyTorch. And also, in a practice, they usually implement it in an architecture critique framework. So they just add more objective function to the orange one. So this is the orange surrogate objective function. And this one is the square error loss for your critique function. And we also add some entropy bonus as a bonus to the exploration. So entropy actually measures the diversity of your policy. And here, C1, C2 are just the two empirical values. And in the paper, people set C1 to 1 and C2 to 0.01. Okay, so in terms of the performance, we have the original surrogate function, and this is the clipping method, and this is scalar penalty method. They tried this algorithm in 21 runs and over 7 environments. And this is the normalized score. And you can see that the clipping method is with epsilon 0.2 is the best overall. And one observation is that the original one is really bad. And they just continuous compare the PPO with clip to other methods. And you can see in most of the cases, PPO performs much better than others. And it's very interesting to find that PPO is actually better than TRPO, even it's a proximal version of it. So maybe the reason for it is the constraint is not so strict. You can actually break sometimes. And also, so I want to introduce some related work of it. So first one is distributed PPO. This paper is from Google DeepMind. And there's one interesting fact is that the paper is actually published before the PPO paper. And the guys in the DeepMind got this idea from OpenAI's talking in the LIPS 2016. And also, second paper is called Adaptive Clipping Approach for PPO. It's very straightforward, right? So in a clipped PPO, you need to set up a constant for this clipping range. So how about we use the same technology or same idea that we keep it as adaptive. So that's the second paper. And they said, like, okay, we can get a better result. Yeah, that's all for the PPO, and thank you.